Alright, hello class. So in this video we're going to be going over slopes of polar equations. So just like with parametric equations, we need to be careful with different types of derivatives when we're working with polars. So recall first of all just notation d something d something. So d square, d triangle means the rate of change of whatever that square is as x changes. So let's kind of look at that relationship here between polar rectangulars so that we can bridge what we just talked about with this and we can really understand what is going on with polars. So this is a point, and there are a few different ways to define points on a graph. One way is rectangular. So you have an x distance from the origin and a y distance from the origin, so horizontal and vertical. You can do that. However, one thing you can also do is called polar. So the distance between those with an angle. So from the origin to there, and then there's an angle that tells us where it is from theta equals 0, which is defined as the x-axis. So let's use this and that to analyze what different derivatives mean. So first one we're going to look at is DYDX. This means the slope of the line tangent to the function. So literally just if we got a point, we found the slope there, that is what DYDX tells us. So how do we find that? Well, recall also, I'm going to rederive the stuff up here. If we look at sine of theta, that's going to be opposite over hypotenuse, y over r. So y equals r sine theta, and then similarly x equals r cosine theta. That's going to come in handy right now. So dy dx. We have functions of theta, right? So we have y equals r sine theta, x equals r cosine theta. So if we're doing dy dx, that's doing ddx of y. But y is a function of theta. So what we're really doing is dd theta of y, and then chain ruling the inside. So the inside has thetas, and we want x in the end. So we just differentiate theta with respect to x. So chain rule. That's your friend here. Chain rule everything. So essentially you can think of it as dy d theta times d theta dx, or you can also think of it as dy d theta divided by dx d theta, whichever one makes more sense to you, and sometimes there's situations where one would be more useful than the other. Okay, so d squared y dx squared. This means the rate of change of dy dx. So it's the same type of thing as second derivative in, I guess you can say, regular functions. Like looking at this, we can tell that we're going to have something that is concave down over around here, and then concave up, concave up, concave down, concave up. So same idea, right? So mathematically though, what's that going to look like? We know that d squared y dx squared equals ddx of dy dx. However, dy dx, this is a function that has theta in it, right? So you'd have to take the theta derivative of dy dx and then multiply, again, chain rule, d theta dx. So you can also think about it as dd theta of dy dx all divided by dx d theta for the exact same reason as the things that we did up there. So just going to box that. All right. Now let's move on to dr d theta, because this is one of the common mistakes that people make when being asked for the slope of the function. They're just like, wait, what exactly are we finding? And then they end up finding dr d theta rather than the actual DYDX that they're supposed to be looking for, which is what you're mostly looking for. So rate of change of r as theta changes. That's what this is really telling us. So if we have a polar function like, let's say, something like this, then we're really looking at little slices like this. If we have a small theta, how much is r changing? And this is pretty simple because r is a function of theta. So you literally just take the derivative of that and then you get it. So for instance, if we have r equals, I don't know, let's say like sine of 2 theta. dr d theta is easily just cosine of 2 theta times chain rule to the inside times 2. So 2 cosine 2 theta. Alright, so let's look here then. So this is an interesting one as well. dx d theta and dy d theta. Essentially, if we're looking at functions, let's just draw something. At each point, we have x's and y's. So you just based on theta, then we're gonna see, let's just say starting from here, going up, and then the next part. So how much, given some theta, is the function going to be moving in the x direction? How about the y direction? That's what this is actually telling us, based on theta though. So these are actually pretty simple as well to find. Similar with dr dx, dr d theta, x is a function of theta and y is also a function of theta. Because remember, r cosine theta, r sine theta. R also has thetas in it, so it's pretty easy to just straight up take the derivative here. Alright, so let's practice with this and try to find some stuff. So, where does R have a horizontal tangent? So you might be tempted to find where dr d theta equals 0, because horizontal tangent is this. However, that's not quite what that is. We actually need dy d theta here, because that's what's going to tell us the actual slope. So notice that this is not exactly a slope. There's just how much is x changing, how much is y changing with theta. Here, this is how much is r changing with theta. And here, we're getting the actual tangent. So the question is, where is this tangent? Okay, so we need dy dx. So for that, we also need y and x. So let's just get y and x first. Y is our sine theta. So that's 1 plus 2 sine theta times sine theta, which is going to give us sine theta plus 2 sine squared theta. X equals r cosine theta. So same thing, just substitute things in, and then we end up with cosine theta plus 2 sine theta cosine theta. This is going to be easier if we simplify it to sine of 2 theta. So I'm just going to do that real fast. And now we want dy dx. So how we get that? Remember, dd theta of y divided by dx d theta. Alright, so that's just dy d theta. So let's see. We get cosine of theta plus 4 sine of theta times cosine of theta. All divided by negative sine theta plus cosine 2 theta times 2. So I'm going to move this because definitely going to need a lot more space. but this will actually bleed together anyways. So all right, so let's simplify this a little bit, make things a little bit easier to work with. So let's see, this is 2 times 2 sine theta cosine theta, so this could be cosine theta plus 2 sine of 2 theta. And then the denominator is just going to be, let's see, so let's just move that 2 in front and then move the cosine in front of the minus. So 2 cosine of 2 theta minus 2. All right, so we want horizontal tangent. Horizontal tangent is where DYDX equals 0, right? So that's where the numerator equals 0. Since we don't need a denominator, that's kind of irrelevant in terms of this. So cosine of theta plus 2 sine of 2 theta equals 0. So 2 sine of 2 theta equals negative cosine theta. Let's see. So it looks like if we actually break this out, that'll be a little bit easier. I'm going to do it over here. So 2 times sine theta cosine theta, or 2 times 2 that, so that'll be 4 actually, equals negative cosine theta. Divide out sine and cosine, and then we'll end up with 4 equals, I'm just going to write this out so that we can make sure that we are dividing the correct things out. It's easy to lose things if you just skip. Okay, those get divided out, so we end up with negative 1 over sine of theta. Okay, so if we work with that then, we basically see that sine theta equals negative 1/4. So theta equals sine inverse of negative 1/4. So you can plug this into a calculator. You'll see a few things come out from here. We want both of the ones that exist on the interval from 0 to 2 pi. So look for that. I'm actually going to just leave it like this for now, and then I'll put the solution in the description. So I want you to try doing that, and then I'll show you the solution down there. All right, vertical tangent. So this is where DYDX is undefined. So let's look at the denominator of it and use it. So we got that. 2 cosine of 2 theta minus 2. So 2 cosine of 2 theta minus 2 equals 0. That's where the function is undefined, right? So 2 cosine of 2 theta equals 2. Divide out the 2's. Then we get cosine of 2 theta equals 1. So let's see. Cosine. So we're trying to figure out where cosine equals 1. So easiest way is just, okay, so 2 theta equals 0 or 2 pi. So what thetas make that happen? We have 0 and we also have pi. Well, does anything else work? If we plug in 2 pi, we're actually going to get 4 pi, which also satisfies this equation. You can check that on your own. But essentially, here are the thetas that work in this case. Alright, so I know that was a lot. It's a pretty long video. I'm going to stop it here since it's gone on long enough. Alright, so hopefully that was helpful, and see you in the next video.